I'm absolutely delighted to be here, and it's a real privilege and a pleasure to share with you some of the excitement and new developments in our understanding of some of the most curious and bizarre objects in the universe, black holes. So to give you a bit of a context, black holes are a key constituent of the universe in terms of how they shape the universe. They are not key in terms of the overall cosmic budget. So the overall cosmic budget of the universe is dominated by two components that have remained elusive. So one is dark matter. So all the matter that we know, stuff on the periodic table, the atoms that we're made of, this is not that stuff. And that is 90% of the overall matter content of the universe. We think it's some exotic particle that formed very early in the universe and, in fact, structures the entire universe, facilitates the formation of galaxies like our own, but we have not yet discovered the particle. We know what dark matter does. We know it aggregates due to gravity, but we don't know what it is. Similarly, the other dominant component of the universe is dark energy, and you may all remember that in the 1920s to 30s, you've probably read about it, that Edwin Hubble, the astronomer, discovered the expansion of the universe. And what that really means is the distances between galaxies is increasing with time. Galaxies themselves are not expanding, but just the distances, so space between the galaxies is expanding. And as recently as 1998, it was discovered that this expansion is actually accelerating at the current moment. And so you need some energy, just as you need the gas pedal to give you some acceleration when you're driving a car. So this energy that is driving the acceleration of the universe, we actually don't even know if it's a real energy, but we think it should be something like an energy. That's called dark energy. We don't know what that is either, but we know what it does. Similarly, for black holes, we cannot see them directly. They do not contribute, a substantial mass proportion of the universe or anything, but it turns out in the last 10 years or so, we've come to understand that they fundamentally shape the properties of galaxies, including our own, and that they play an outsized role, given how tiny, how compact they are on very, very large scales that you would not expect them to actually act upon. So this is sort of the current inventory. And the reason I've clubbed all of these three exotic things in the universe is that none of them are directly seen, as I just mentioned. They're all indirectly mapped. But we have very, very powerful evidence for the existence of these three components. You might say, well, is this like ether? It's just going to go away. No, and I'm hoping to show you, at least for the case of black holes, where we are. So before that, let me give you a little bit of a setting that will help you understand these really bizarre objects. So first of all, in order to understand what black holes really are, we need to understand how we think about the universe. The universe is basically imagined, thanks to Einstein, as a bendable fabric. You can think of it as a fabric that is stretchy, and what causes the stretchiness and what causes divots or little potholes in this fabric of space-time is matter. So any kind of matter will cause a divot or a little pothole in space-time. And in fact, it was this remarkable insight that Einstein had, this kind of relationship between the nature of matter, the shape of space, and as it turns out, Einstein's equations then actually tell you how things will evolve in the universe. So I just want to remind you that the entire universe is envisioned as this sheet, and it's a four-dimensional sheet where you have 3 dimensions of space and you have 1 of time, because in the universe, distances are so vast, even though the speed of light is very large, we need to know where an event occurred, because it takes a finite amount of time for the signals to reach any other part of the universe. So what is the relationship that Einstein helped us figure out between mass and space is that the presence of mass fundamentally alters the shape of space or the geometry of space. If there was no matter in the universe, our universe would be like a flat sheet. So for example, when we know that that's not the case, our universe has, I just showed you the inventory, so we have matter and we are here. So for example, if you look at a celestial body like the sun, that's what the sun does to this sheet. I just want to remind you, right, there's nothing above the sheet, below the sheet. The entire universe, we are all on this sheet. And so the sun causes this pothole that you can see that's shown in this cartoon. a neutron star, which is much more compact than the sun, so matter is packed very tightly, much more tightly than the sun, causes a much deeper pothole. Whereas a black hole is so compact, so dense, that it causes a puncture in space-time. So that's what a black hole really is. And so when we say a black hole, black hole started out life as a mathematical solution to Einstein's equation. And what that really means is that Einstein's equation tells you how to relate matter to the shape of space that matter distorts. And so when I first started, I've been working on black holes since my PhD thesis in Cambridge. And when I started first writing the book, I wanted to look at the history of the term black hole. So it turns out that led me back to Calcutta, surprisingly. And in 1756, it has nothing to do with astrophysical objects. It had to do with the place of no return. It was the name given to an infamous prison where the Nawab had imprisoned the officials of the East India Company who perished overnight. So it was a place of no return. And it turns out the astronomer Wheeler, 1960s, realized that this was a very apt term to describe the properties of astrophysical black holes, and that's the source of the word. So to understand why these objects are enigmatic, right? So take, for instance, what happens to light. You might have all heard that not even light escapes a black hole. So this is why, because of the shape of space, you see that light that strays near a black hole can have one of three possibilities. If it's just grazing far away, then it gets a little bent and then it sort of escapes. And so you would skirt the black hole so you could see sort of the light sort of skirting the edges and sort of escaping. Now, there's a very interesting sacred boundary called the event horizon for a black hole. Every black hole is characterized by an event horizon, so it's kind of the region of no return. Once a beam of light or matter or anything goes past this event horizon, it never makes its way back out. And then there's this interesting space in between the two where light is only deflected versus light is swallowed, as it were, by the black hole. You have this region that is called the photon radius or light orbits, where light will perpetually be caught there. So it's like Dante's limbo, sort of purgatory, right? You're sort of trapped there. And so these are the effects of black holes that we can now see. So these were the mathematical properties. And now, over the last 30, 40 years, black holes have really become real. And in fact, we've been able to map all these properties, see the effects of all these properties. So let me first show you that black holes are real. So this is the Hubble Space Telescope image of a galaxy. We're zooming in. We now believe that every galaxy, including our own, harbors a black hole in the center, and a supermassive black hole at that. A supermassive black hole is just one that's about a million times the mass of our own sun. So what you see here when we are getting to the heart of the galaxy, this is a region, this is an artist's impression. So we haven't quite made it down to resolve there, but we know in terms of physics what's happening there. So what we really see, this red stuff that you see, is the feeding disk of gas that's going to fall in. And the way we see black holes, and it's lit right around the center in this cartoon to give you a feeling for how we know the black hole's there, because we detect the dying gasps of the gas. It's been pulled in by the intense gravity of the black hole, and it gets heated, and it starts to glow. And that's what we see. And that's how we know there's a black hole there. And often, as shown in this cartoon, black holes can also spew material out, energy and material out, light and particles. So that's a jet. And so that is actually also seen in real black holes. So aside from that, black holes, when they are feeding, so when there is this gas disk and the material is draining from that disk onto the black hole, we believe that black holes are feasting. That's when you see them. And in fact, these correspond to some of the brightest objects in the universe. They're called quasars, and we see them out to the farthest reaches because they're like cosmic lighthouses. They're really, you can see them, they're very, very bright. They outshine the galaxies that they sit in. And then it turns out that there are black holes, like most of the black holes in the nearby universe, that are actually fasting. Either they have evacuated and gobbled all the gas that's around them, so there's nothing left to pull in, or somehow the gas has properties that prevent it from being sucked in, as we'll see. So, for example, the black hole in the center of our own galaxy, gas is too hot, there's very little gas left, and that one is fasting. So in terms of the incontrovertible evidence for black holes, I've been sort of stressing to you in the last 10 years or so, we actually know this is not going to go the way of ether because of all this evidence that I'm going to be leading you through. So this is one of the most compelling pieces of evidence for the existence of a black hole in the center of our own galaxy. So this, what you see there, the little twinkly stars and the orbits are actual orbits taken over time of the stars around the Milky Way black hole. And so you might see this little red blob. This was a blob called G2. So this was a bit of gas that we thought could get trapped in. Alas, it had a near miss, and it's going to come back out in 2035, and it'll be gobbled then. So we're waiting to see if this little gas blob would actually come close enough, stray close enough to feed our black hole and jumpstart its feeding. So it turns out it didn't happen. But those orbits that I showed you, right, so that's real data, and that data has been taken by two independent groups, one at UCLA led by Andrea Goetz and one in Germany, and they've been following the motions of those stars, and you might have noticed that they beautifully fill out ellipses. Like Kepler's laws, you kind of figure out where the black hole is because there's so many ellipses that close, and you know that the foci of the ellipse are where the gravitating mass is going to be sitting, just like the solar system. We know where the sun is and all the orbits of the planets. And so that is still far out enough. So the stars that we saw there, it takes about 17 to 20 light days for light to travel that kind of distance. And this is at the heart of our galaxy, and we are way far out, right? So at where we are in the solar system, we're really not impacted by the black hole. But the assembly of our galaxy has been fundamentally shaped by the properties of this black hole. So just to show you the large scales on which black holes exert their influence, even though they're tiny, they're compact. So this is real data and X-ray and radio data from a galaxy. What you see in the optical of the galaxy is that dusty galaxy that you see spread across. You see these huge gas jets. And these are big radio lobes that are glowing in the radio. This is material that we believe has been pushed out by the black hole. I'll come back to this at the end. So this was a big puzzling problem, even when I was doing my thesis about 15, 20 years ago. How does the black hole, which inhabits a tiny bit portion of the galaxy, central piece of the galaxy, actually impact the larger scale environment? And we knew that the black hole impacts the environment because there are correlations seen in the properties of black holes, like the mass of the black hole and the environment, the galaxy that it's sitting in. So bigger black holes seem to be sitting in bigger galaxies. And so why is that? So it turns out, and how does that work? I mean, that can work only if the black hole is somehow coupled over a range of physical scales that appears quite unnatural to start. So one of the other most compelling pieces of evidence, most of you saw this image, I think it was like on the front pages of most newspapers around the world, is the Event Horizon Telescope image of the black hole in a nearby galaxy, M87. And so what you're seeing here is that cartoon that I showed you with light orbits, the light in limbo that is trapped around the black hole. So what you are seeing here is the entire sort of disk of gas that is going to actually fall in, that is swirling around and held, and you're seeing the light. And in fact, you're seeing all the light that is reflected because there's extreme light bending because of the gravity of the black hole, that you almost like you're seeing the back of my head. You're seeing the backside as well. And so you see this image, and you all know that this was an incredible technical feat to do this, to resolve all the way down, because I started off showing you a movie when I said, well, we know there's a black hole there, but then when we get to the center, I'm like, oh, that's an artist rendition. So this is as close as we have ever gotten to a black hole. And it was done very cleverly by leveraging existing radio telescopes on Earth, 8 to 9 of them, and sort of camouflaging them and using them to have the dish, the entire Earth, appear like one dish. So it was very clever technically, as well as... So I was not involved in the project. I was just an ardent supporter. But, I was thrilled when the announcement was made, and I was, in Washington, D.C. So that's the PI of the project, Shep Doleman. And for those of you who are interested, apparently there is a cocktail called black hole. I didn't believe it, so somebody sent that to me as proof. So what do we really know about black holes? The kind of the work that people like me and many research groups around the world are trying to do is to try to figure out the correlations between black holes, the properties of the black holes, the mass of the black hole, and the galaxy, the host galaxy, the parent galaxy that they're sitting in. As I mentioned earlier, there appears to be a correlation, so bigger black holes, bigger, brighter, bigger galaxies appear to harbor bigger black holes. So the question is, how does that happen? How does the black hole know about the galaxy and vice versa? Well, fundamentally, it kind of makes sense because we know that gas is the ultimate source from which stars form, and the black hole is fed. So at some level, it's not surprising, but the fact that they are so tightly correlated has been an open mystery. So that's one thing that people like me have been working on. The other thing that I'm working on, I'm very interested and excited about, is the number of quasars, these feasting black holes that we're detecting out to the farthest reaches in the universe. So in that plot that you see there, the vertical is the mass of the black hole, and your eyes will pop when you see that's like 1 billion, 10 billion solar masses times the mass of the sun. And on the horizontal is roughly the distance from us. So the bright green things that you see are really farthest away. They're so far away that the universe at that time was 10% of its current age. So understanding the origin of the first black holes and how those really massive black holes, billion times the mass of the sun, were in place so early on is really where the frontier is. And so me and my research group have been pushing on that question for the last 10 years, and we're going to have some really exciting results validating theories when the James Webb Space Telescope flies, which incidentally I want to mention assembled perfectly well a couple of weeks ago. So it's a go, and hopefully it'll be on time. So the question of what the seed black holes are, what are the initial masses of the black holes, is the big open question in the field right now. So traditionally, we believe that the first stars will consume the fuel, die, and leave a little black hole as a remnant. But those black holes are too tiny to account for the billion mass behemoths that we see already in place in the very early universe. So you need a way to maybe make black holes very massive seeds from the get-go. So that was the idea that we proposed a few years ago that stands to be tested by James Webb Space Telescope data, and those are called the direct collapse black holes. So they start out life already massive. And the idea is very simple, is that you have gas that really assembles very early in the universe into a black hole that is about 10,000, 100,000 times the mass of the sun from the get-go. And then growing it to 1 billion times the mass of the sun is not that hard. Whereas if you start out from a seed that's about 10 times the mass of the sun, and it's very, very challenging because you don't have enough time to feed it fast enough. So how do black holes actually grow? So I've sort of given you a glimpse that, how are they born? So how they grow is by feeding onto gas. And we believe that structure in the universe we know grows by the collisions of galaxies. So this is a simulation from one of my students' work where you see two spiral galaxies, rather like our own, if you will, and they have a growing black hole that's flickering. It's flickering because it's feeding, okay? It's not fasting. These are feasting black holes. And you'll see that we know that structure in the universe in terms of bigger galaxies get built up hierarchically. So two small galaxies will collide and make a bigger galaxy. The early universe is a very violent place. So, but what happens to the black holes in the center? Well, they also eventually merge. But now come back to thinking about what I told you about black holes. One way to think about them is punctures in space-time. So what does that mean? What does that mean when two black holes merge? So it turns out that when two black holes merge, there's an absolutely fantastic set of fireworks that happens, especially these supermassive black holes. But before I show you exactly what happens when two supermassive black holes merge, let's look at it visually from top on down, right? So there's a supermassive black hole in that. It's a speck in that black region in the center. It's a top view of that merger of galaxies that we saw. This is the final stage. We're looking down, and we have gas that is piled up like a disk around. Okay, for some reason I couldn't get that to work, but hopefully I'll get this to work. Yeah. So these are two merging black holes. As I said, there are fireworks of all kinds. So one of the interesting things that happens is that two black holes, when they merge, they actually cause a tremor in space-time itself. And these are called gravitational waves. And for supermassive black holes, because they're sitting in the centers of galaxies, accompanying this final earthquake and shaking of space itself, before that, because you have a lot of gas, and we just saw when those two galaxies merge, you see a lot of other electromagnetic fireworks. You'll see X-rays, you'll see radio waves, infrared. So we will get signals that say, something's happening there because we'll see a flare. And then we'll detect these gravitational waves. So gravitational waves, as you all know, have recently been detected for the collisions of small black holes. I'm more interested in sort of the obese cousins of the black holes that were detected by the LIGO collaboration, and you must have heard of that recently. So again, I want to showcase some work that one of my current graduate students just wrapped up. And this is to show you that we build storylines. So we built a storyline. The things that are shown as stars are actually black holes. And so this is following the life cycle of black holes from birth to where they would end up today. And the clock that you see there, the strange numbers there, z is equal 0 corresponds to today, and that is redshift for those of you who know. So, and what you see as black specks are the real data, the measurements of this. So this is the relationship between black holes. Remember I mentioned the correlation between black holes and the galaxies that they that harbor them. So the tremors in space-time that we're likely to detect from the collisions of supermassive black holes will be detected by a system of satellites. You need that to be out in space rather than LIGO, which consists of apparatus on the ground. So you would need this configuration, and this satellite has been planned by the European Space Agency, and it's called LISA. NASA has bought into it. And I happen to serve on the NASA LISA science team at the moment, trying to figure out what are the big science questions that can be answered with that mission. Meanwhile, let me quickly wrap up showing you that we know that black holes will collide, and we know that they will create tremors in space-time because the LIGO collaboration detected the collision of stellar mass black holes, 10, 30, 50 times the mass of the sun, colliding with another small black hole. That was another huge challenge, and it was not a one-off, and in fact, the detectors were turned on very recently, and we're detecting a merger almost one a week. So the universe is replete with black holes, small and big. And so though they don't contribute majorly to the mass inventory, as I mentioned, they are really, really important, as it turns out, because of the observable effects that they exert on galaxies. So this is just a cartoon showing how the LISA mission, those three satellites, that configuration, and what really will happen is that the earthquake, the tremors in space-time will be detected by those three satellites, and they'll be able to triangulate and figure out properties of the black hole. So I just want to wrap up so one of the reasons I wrote the book and that I'm really passionate about writing as well is because I think some of the most complex ideas in science are actually quite simple when it comes down to it. And I think that, there's a lot of mathematics to go at a deeper level, but the basic conceptual things are actually quite easy and straightforward, and they're very, very accessible. And it's very, very exciting time to do science right now because within one lifetime, a single scientist's lifetime, you can propose an idea. It can be verified, validated, or discarded with observational detections, with evidence. And that whole cycle can happen within one lifetime. So I just want to close with something very, very exciting that happened late last year. So when I was a graduate student in Cambridge in 1998, with a collaborator, Stein Sigurdsson, we wrote a paper. So, I was intrigued. This was when we had just detected this correlation between the small scales on which black holes operate and galaxies that spread out on very large scale. So we didn't know what the origin. Is that just correlation, or is there some causation? If there's causation, there has to be physics, right? And so I came up with this, cute idea. I said, well, one possibility, this was when it was not clear there were outflows and so on, right? It was 1998. We've learned a lot since then. So we had sort of had this suggestion where we said that if it's a quasar could possibly drive an outflow. Material could push material out. And so there would be shells of material that would be pushed out if the quasar, a black hole, was able to do this. And so then I realized that material that's pushed out could be detectable. The fact that this material was being pushed out, it was heated up, it would emanate radiation, and that would be detectable. And so we made this prediction and what was interesting about this was the wavelength at which you would see the glowing. So this would not be ultra hot like X-rays. It would be very sort of, in cosmic terms, not very hot. So you would see it in radio waves, right? So not much energy. But you would see it in 900 gigahertz. So this was a frequency at which we did not have any equipment at that time. But it was in the works. So there's a detector called ALMA, which is an array of radio telescopes in Chile that has since been built. And so, made a prediction. And I said, well, if there was such a telescope, it would see that there would be a patch. It would detect a patch there. And you would see an asymmetric patch because of the viewing angle, even though the quasar itself might push things out symmetrically, when we sit here and watch from the ground, we might see two asymmetric patches. So, I was aware that this telescope was being built, but, I'm not an observer, so I was not, actively looking to go and validate this idea. So late last year, I got an email from a colleague, Mark Lacey, and he said, guess what we found? We found an outflow. And we found it in ALMA, in radio. And I think what was exciting for me personally is the fact that, it was just a cartoon that I drew, but the configuration they found was uncannily similar. So I can't tell you how thrilling it is to be alive at a time when you can actually do this. You can make a prediction. It's taken seriously enough by your colleagues, of course, to test, and that it gets validated. So I just want to close and say that, we live in a very, very interesting and strange time, but as I'm just showing you all the amazing stuff we've learned in the last decade about like one corner in astrophysics, just black holes. And a lot of the work is done in the United States, but we, of course, in collaborations across the world, but the US has been leading. And this is also the country where denialism of science is most rampant. So it's a bizarre, bizarre time to be alive. And I often like to close and say that I think, the universe and our significance and insignificance in the universe of this. It's significance because we can figure all of this stuff out. We have a little organ in our skulls that has helped us figure all of this out. And we can also fundamentally shape and reshape our planet and have put it in peril. And if you look at the cosmic scale of things, we're a tiny speck, right? There are 5,000 other planets around other stars, right? But I think this is a critical time, and I think we should all pay attention to science evidence and enjoy the exciting results and discoveries, but also realize that we have a responsibility, having had the capacity to figure this out. Thank you very much for your attention.
Wasn't she terrific, folks? Yeah.
Thank you.
Make sure you go out, get her book, and I want to just ask you a couple of things about what's going on in kind of the news and science and space. I can't not but start with Space Force.
Yes.
Talk about that, please. Save us.
I don't think we need Space Force. What we really need, though, is trying to understand the fact that as humans, we're going to try to colonize space. So how do we regulate, how do we understand who gets to launch vehicles, communication satellites, who gets to use space, because space is getting crowded, and especially low Earth orbit, there's lots of debris. So I think there's definitely room for like a global understanding of how to use space as a resource. But it's not clear to me that space defense is of the highest priority. And
framing it in this kind of militaristic way is not a kind of a European Union of the space. It's kind of the opposite, right?
That's right. And I think that the military-industrial complex has been has funded a lot of basic sciences, but we now know that is not a prerequisite to fund basic science. Right. So I don't think we need that. I think I would rather that the money was put into basic science.
All right. No, that's very helpful. Please get your questions ready for Priya. I want them to know about a little bit of another scientist who many of us who are not scientists read and kind of understood a little bit about the universe, Stephen Hawking. Yeah. Your work with him. Tell them a little bit about it.
So I had
Who knows Stephen Hawking here, right? Everybody, right. Yeah. So she's going to tell you.
So I did not actually work directly with him, but he was a very strong supporter of my work, and I overlapped with him in Cambridge. And it was quite challenging to actually converse with him, as most of you have seen, because it's very different from the cadence of an actual conversation. So one of the scariest moments I had with Stephen was that I gave a seminar. So he would keep track of he was very interested in black holes, especially astrophysical black holes. And my advisor was one of his, colleagues. They were quite competitive with each other, Martin Rees. And so anytime Martin had a student who was working on black holes, Stephen had to be in. He needed to know what was going on. So he would come, and he came to one of my seminars, and he was there. And this is the dreaded moment, right? Suddenly you hear from the voice, "No." And I freaked out. I was like, oh my God, did I make a mistake? Did I say something wrong? And so I just froze for a few minutes. And then it turns out that actually his no had nothing to do with me. He was having this conversation about his lunch with his, and he had said no to something there. But there was a moment where I was like, oh my God, have I made some error? No, it was a real privilege to have had the chance, and it was kind of sad. I was at his funeral. It was sad, but I have to say that people never expected him to live beyond 40 max, right? And the fact that he was remarkable. There was not a moment of self-pity. There was not a moment of kind of dwelling on his inability to function like everyone else. He just had an amazing mind, very sharp, and very naughty as well, I have to say. Yeah, very funny, but also very naughty.
Yeah. Let's get a question, yeah. Please tell us who you are, yeah. There's a microphone coming. We're live streaming.
Thank you very much for the presentation. My name is Devesh, and I have 2 questions for you. First is, for a layperson like me, could you explain what is the human benefit for understanding everything you do about black holes? It seems intellectually very inspiring, but at a personal level, I can't connect to it. And the second question I had is about asteroid mining and what a lot of these companies are doing. And it's hard enough to define property rights on Earth. How are you going to define property rights elsewhere?
All right, we got good question.
Yeah. So the first question, right? Will all this understanding of black holes change your life, your day-to-day life? No. However, the mathematics and the physics that has been developed in order to reach this kind of understanding, and the computational facilities that have been developed, all the sort of the progress that has happened in all of this does impact other fields. So, for example, the imaging technology that was needed to reconstruct that image from the Event Horizon Telescope collaboration that you saw this April, right? That stuff is state of the art, and within a decade it's going to get into medical imaging, right? So that kind of using very sparse data to reconstruct as reliably as possible a big sort of comprehensive synthetic image. So, there are many, many fields where those techniques are obviously going to be adopted. So right now, algorithms from many other fields were used, and they were refined, and they've pushed the work forward. And the question about asteroid mining, no idea. I mean, I think there are people who are starting to talk about what are the rights and who has the rights, and then how do you get the stuff back, and so on and so forth, right?
Okay, 1, 2, 3, go ahead.
Yeah, thank you very much, and kudos to everything that you do. That's
thank you so much.
Fascinating. You talked about when the 2 black holes collide,
merge.
That there's actually like an earthquake. Do we feel that in any way in our...
Oh, no. So, we're talking, these are gravitational waves, and they're so feeble. They are so feeble that it took 40 years to build the apparatus, this LIGO, to actually make the detection. And the way in which you detect it is when a wave goes past a detector. So in the case of LIGO, the detector had perpendicular arms. And so the wave would pass through one and not the other. And you would detect the difference in, so there was a laser beam that was going back and forth, and you would detect a small difference in the travel time for the laser beam that would be affected by the wave passing through. And that's not enough, because a lorry or a truck going by could also cause that little bit of a deviation. It's a very tiny deviation. It's the equivalent of like a subatomic level difference that is being detected.
We're safe. We're safe when that happens.
Well, we're very safe. Actually, even dark matter, we are totally safe, because dark matter goes through us all the time. And it does nothing, which is why it's so hard to detect. Thankfully, it does nothing. Imagine if it reconstituted us going through, right?
Okay, who has the microphone? Yeah, go ahead.
First of all, congratulations.
Thank
this
you.
is Sumit Ganguly. The question is your comments on Higgs boson, the God particle. As an extension to that, how do you reconcile your own belief in spirituality and what you do as a research scientist?
Yeah, so I actually believe that science and religion are two completely different things. And to mix them up is like making a category mistake. So it's like saying, how salty is the color blue? Right?
Very.
So I
obvious,
think,
yeah.
I think science is trying to. This is how I see things, right? And therefore, I don't see it as a conflict in any way. I don't see them. They're not trying to do the same thing. They're not trying to do. Science is trying to give an account of what we see, what we can measure, what our sensory apparatus can actually infer from that, right? And spirituality, religion, and systems of belief are giving you reasons for, explanations for, that are very different from, they're not the same kinds of explanations. They are things that are trying to help you make sense of your life and make sense of what you're figuring out and why you're figuring it out.
Okay, one more question, yeah.
Hello.
Sorry?
Can you just take the mic and then
Can you take the microphone,
we'll have
sorry?
both of you ask questions together. We'll take your questions too, sir.
My name is Dr. Chandrasekhar, but I'm talking about S.
The others,
Chandrasekhar,
yeah.
who had been working on this black hole. How far?
Oh, absolutely. Yeah, no,
So
no.
how far have we come from that? And let's get one more question.
We've come really far from there. So when Chandra was working, it was unclear that black holes were actually real. They were believed to be mathematical solutions, and his theory of stellar evolution and the end states of stars suggested that we should find black holes. And it was only in the 1960s that we securely detected those objects. So we've made enormous progress since then. And yeah, I mean, he is an enormous inspiration for me. And I inadvertently followed his footsteps by going to Cambridge and studying at Trinity College. And
What advice would you give a 7-year-old who aspires to become an astrophysicist?
Yes. So for the young people, I think that was part of, I didn't want to sort of set them apart and say, for the young people in the audience, I just want to show you how exciting science is. But I think that astrophysics is an absolutely wonderful field to be in, because every day you figure new stuff out. And everything that you figure out is not going to be a major discovery in the universe, but it's a personal discovery for you. And that sense of personal discovery is, incredible. And I think that a life in science, that's what is exciting. I am partial to astrophysics, but I think, genetics, neuroscience, there are many, many fields that are really in a wonderful stage at the moment, where every day groups of people are figuring something new and fundamental that we had no idea. And our understanding has advanced tremendously. And in terms of advice, I would just say, read. And, you're so lucky that now there's so much good material available on the internet. So watch PBS shows. And there are lots of games and things you can do. So, for example, there's a very fun game where you can look at what happens to objects when they're flung towards a black hole. And I can tell you offline how to get access to that. So there's a lot of learning material that is super fun right now.
Before we go, I want you to tell them what your Twitter handle means, and also about your connection to one of the most important literary prizes in the world and how you're involved with that.
Right. So so for the longest time I did not join Twitter, and Sree had been telling me, "Oh, come on, you've got to join, be in the 21st century." I'm like, "Oh, but I don't know how to figure out a handle." So Priya was taken, Priyamvada was taken, Astropriya was, all possible things were taken. So I have, one of my close friends is Brian Schmidt, who won the Nobel Prize for the discovery of dark energy, and I was in Australia. And I said, Brian, he said, "Come on, you've got to be on Twitter." I said, "I don't have a handle." So he said, "Okay, I have a suggestion." So he and another friend, Sean Carroll, who actually has a new book out on quantum mechanics that just got published last week, they said, "Look, we came up with shear Priya." So the other thing that I work on is the bending of light by gravitational lensing, and that shears the shapes of galaxies. SHEAR. So there was a play on words. And then Brian also noticed, he was always teasing me about, how famous I am, and how you just have to say Priya, and everybody in astrophysics knows who that is. Whereas he, who is a Nobel laureate, if you say Brian, they'll be like, "Which Brian?"
Brian Greene.
There are like 500, exactly. There are like 500 other Brians, right? So the sheer Priya was that the fact is that you just needed Priya.
And you're HWER. Yeah.
That's right.
Okay, and literary?
Oh, yes. So the JCB prize for literature is the new prize, that's literary prize that was launched in India last year. And what is special about this prize is that it awards books that are not just written in English, but also books that are written in many of the regional languages in India and are translated then into English. And it's one of the biggest purses for literary prizes right now. And it finally brings to the rest of the world this incredible tradition of writing, regional writing in other languages, other Indian languages that was inaccessible to readers in English. So I was very fortunate to be asked to serve on the first jury of that prize.
And how many books did you have to look at? I remember
I
it was a
read
lot.
57 books over 3 months.
You thought you were busy. Ladies and gentlemen, Renaissance woman, Cheer Priya.
Thank you.